In this screencast we present LogAn, a tool we developed on request of a number of Belgian machine builders. LogAn allows them to make better use of their log files. The main part of this screencast consists of a live demo, but allow me to first briefly explain you why log files are challenging and what LogAn can do to simplify also your log analysis. We all know that machines contain more and more software and that they usually produce logs. Developers use those logs for debugging, service personnel analyzes machine usage, managers want to collect production statistics and so on. Unfortunately, those logs are often very complex, in the sense that you need a developer to interpret them. And even those experts sometimes get lost in the log, because logs have no clear structure. They are a flat list of events, and it is, for instance, difficult to look for relationships between log lines. Even issues that you have seen 100 times before are not immediately recognizable in logs. So let's take a look at an example. This is a simple log containing typical timestamps and log messages. This log is produced by a test machine, and the machine first clamps the object to be tested, it then performs a test step, it stores the partial results for that step, and finally it saves the overall test results in a database. During that save operation it assigns a sequence number to each test, in this case 31. Now, what are people typically looking for in such a log? A trivial query would be to count the number of performed tests, for instance. You open the log file in Notepad++ and you count the number of lines containing the string clamping object, and you have the answer. And that's quick and that is trivial, so nothing special about that. It becomes a bit more tricky when you want to detect a new production batch. And each new batch starts with the sequence number 1. Unfortunately, this machine sometimes has a communication issue, so the sequence number 1 or even 2 could be lost. As a consequence, your only option is to look for drops in a sequence number. If you are, for instance, at sequence number 500 and it suddenly drops to 4, you know that a new batch has started and that the first 3 sequences were lost due to communication issues. There is no easy way to solve that with Notepad++ or any other plain text editor. Still a bit more annoying, when did an operator hesitate more than 2 minutes between tests? This could indicate that he had problems inserting the object into the machine, so it could be relevant to optimize the production. To answer this question, you should look for a gap between the save operation of a test and the start of a next test, and then mark all those gaps that exceed 2 minutes. This can be solved by writing a script, but you feel that the complexity is increasing here. Similar, there are other more complex queries, like for instance, how many tests does each batch contain? This already supposes that you know the concept of a batch, that you have identified the batches, and that you are counting now all the tests that occur in such a batch. You could reuse the batch script you created previously, and you can now extend it to get the answer to this question, but that doesn't feel fully right, it doesn't feel easy. Yet another one, we know that a machine can lose communication, so tell me how many times the communication has been lost. And that's very difficult, because in that case you have to search for the absence of information, which is not typically something that you do with a filter. But of course you can write a script for all of these questions, but we have felt that it becomes very inefficient to do so. So how does LogAn help? We've built LogAn using techniques for complex event processing. This provides advanced ways to express your queries. In addition, the user interface assists the user in defining and managing the queries. So as a result, you will see that LogAn allows for easier navigation through your logs, and it allows for answering more complex queries, and also non-experts could be executing predefined queries. The demo will clarify all that. Let's take a look at the LogAn application itself. When you open LogAn, you arrive in this empty screen. Here on the left you find the workspace. This is where you manage all the LogAn specific data like parsers, event types and patterns. You will see that happening in a minute. On the upper right hand side you can switch between different screen modes, and depending on the task that you're performing within LogAn, like playing certain patterns, editing patterns, debugging your queries and so on. All the rest of the interface will become clear along the way during the demo, so I will not explain that up front. Before we start the first demo, just one slide to introduce the first step we need to perform, and the creation of a parser. Our machine spits out plain text, while LogAn expects events. For now we are interested in the events we introduced before: clamp on, test start end, store start end and the save. We switch back to the LogAn application and get started. We go to the workspace, right-click the empty area and select New Parser Definition. All the information in LogAn is stored in packages, so we call this package a log package since we are processing our log. We call our parser test machine because we are parsing a test machine. LogAn supports several kinds of parsers, but for this screencast we use the rule-based one. And finally we assign it a friendly name. LogAn now proposes us to switch to the editing perspective because it is more convenient to edit the parser in this perspective. So let's agree to that and we are ready to start defining our parser. First thing now is to load an example log file. Voila, this one will do. We see that the test machine parser is now inside the workspace on the left here. The screen size is a bit limited, so let's reorganize it. And here we have the contents of the log. You recognize it from the slides, clamping the object, test start end and so on. What could our first parsing rule become? Well, we see that every line starts with a timestamp. It is already useful to collect this timestamp for all lines. So we define a rule process date. LogAn offers several conditions to indicate when the rule has to be executed, but this rule has to match on every line. Next we can define what action needs to be performed when the rule matches. Here again LogAn offers quite some choices, but now we are interested in the date time parsing. Once parsed, we would like to store the value in a variable called timestamp. Next we specify the format of the timestamp. The default suggestion is the XML timestamp format. That looks close to what we have here, but the T has to be removed in the middle. So we could even specify what to parse from which position to parse and so on, but we can leave that empty. By default LogAn starts parsing at the start of the current line, and that's exactly what we want to have. So let's try this limited parser now on the log file and see what happens. Yep, he wants to save our changes and voila. It seems that the rule has been performed on every line and that it has produced a timestamp in each case. As a second rule, let's look for clamp on. In this case the rule should only look at the lines that contain clamping object. And of course now we are not parsing a timestamp anymore, but we want to create an event. The list of events is still empty, which is logical, since we didn't define any yet. This brings us back to the workspace, where we again click with the right mouse button to create a new event type definition. We give the event a relevant name, and for now that's it. So now we have this event in the list, and we still assign it the previously collected timestamp as its start time, and we are ready to try our rules again on the log. Voila. Seems to have matched here. And here, or we can even navigate to the next one like this. Let's now skip a bit of work, since the definition of the next rules is almost identical. Step on, step off, store on, store off, till we come to a interesting one anyway, the save rule. Here we want to extract the sequence number from the log line and store it in the event. This can be done by matching the line with a regex filter. To avoid typos in the line, we just copy and paste it. Voila. Remove what we don't need and replace this fixed number 4 with an expression that matches any number. If you're new to regex, this could look a bit confusing, but this is a standard and powerful search expression syntax. The parentheses around the expression indicate that we want to capture the matched value for later use. In this case we want to capture the 4. Again, for this rule, we want to create a new event, and again we create a new event type and we call it save, which now has a property sequence number of type integer and the default value of 0. Take it from the list, assign the timestamp as usual, and take the first matched group for the sequence number. We try it on the log. Some matches. The parsed sequence number is 4. Nice. At this point in time, all interesting lines are parsed and converted to events. It could be interesting though to also have the other lines visible in LogAn without the need to define a specific event type for each one of them. Like you see here, reading from 29, in fact we don't need it, but it is useful to see it anyway. So we can do that easily by creating a new rule and call it, for instance, catch all. It matches always and creates a default event. Let's call it base and give it one field, text field of type string, and it's empty by default. Now once we create the event, we again set a timestamp, and for the text we take all the text starting at position 24. All scripting in LogAn uses this syntax, which is the Python syntax. Try again on the log, and yes, we now have all the lines covered, for instance here, reading from 29. This finishes the parser, so we can go back to the normal play mode of LogAn, open an event source and read it into the buffer using that parser. So you now see the full contents in the buffer. Maybe this base dash part is not that beautiful, so LogAn also allows you to define your own template in visualizing events. So in the event type definition of the base event, we can specify that it just has to show the text and nothing more. Voila, like this. The save event still shows the sequence number in the generic way, so the change didn't affect that. Right, so what did we see till now? First, you saw that we have created a rule-based parser definition. We have defined several actions, selection from a list of a lot of predefined actions. We also have free scripting capabilities there. You saw that the way of creating the parser was through an interactive what you see is what you get editor, and this parser is now reusable for all subsequent logs. Now let's define our first pattern. And we want to see all tests in the log, each one of them starting with clamp on through the final save event and all the relevant events in between. Again, we start from the workspace, we right click and now we create a pattern definition. The package name is a free choice, so in this case let's call it analysis, since we are analyzing information instead of just parsing a log. For the name we can write test pattern. Here also LogAn refers us to the edit perspective because the creation of patterns is easier in that mode. You see several tabs here, but for the screencast we use only the most relevant ones. The first thing a pattern needs is a match provider. It looks for matches in the log. In general, two types exist, but for now we take the Esper main statement, which refers to the underlying Esper library from Espertech. We now need to specify which events we will be looking at. Well, that is in fact everything we have been defining earlier except for the base event. As a next step we choose the pattern statement kind. The different selections here go beyond the scope of the screencast. Just remember that we take a pattern stream here and that we can edit the pattern stream on this last tab. So, what are we looking for? We are looking for a series of events. In LogAn this is represented by an expression kind called followed by. So let's drag such an expression into the editing area. Inside a followed by expression we can add filter expressions that match on a specific kind of event. Obviously, the first event we want to match is a clamped on event. If it matches, we assign it a name, clamp on, for future reference. Once a test object is clamped, the machine performs a test step on it and it saves the partial results, and moreover it could repeat those. So let's define that here also in the screen. Let's draw that, a new sequence of 4 filters. And the first being a step on, then a step off, a store on, and a store off. And we assign them all a name for future reference. Since the machine can repeat this 4 filters any number of times, we have to indicate that here on that followed by expression. We will lower the lower bound to 0, because sometimes no steps are performed at all, and the upper bound we will put it to unlimited, which is specified by -1. This loop will now keep collecting matches till we finally encounter a save event. So we put a filter for a save event here inside the until part. Well, this should work, but it will work only once. LogAn will stop right after the first match that it finds in the log file, unless we ask it to start looking again. This can be done by setting the every flag to true on the outer followed by expression. That means that once a previous save has been matched, LogAn will look again for a clamped on event. So we have now defined what we are looking for. Next, we want to tell LogAn what to do with such matches. We define a match handler for that purpose, below here on the tab. Since we have been matching a full test, it would be useful to generate a new kind of derive event, being a test event. For this purpose we have the event generator. Of course, we cannot just generate any of those base log events, because that makes no sense. Instead, here we will create a new event type definition, and we call it test. We assign it a property, and we call the property the sequence number for that test, which is of type integer and which has a default value of 0. Voila, finished. So now the event generator can generate that analysis test type. The start time is equal to the start time of the clamped on event, so we type clamp on dot start time. And for the stop time, we take the last one, being the save event stop time. For the sequence number field, we just take the sequence number which has been stored, or which was stored in the save event. And for sub events, we indicate which events this new test was derived from. This can be done automatically by clicking on the fill from stream button. Now let's switch to the play perspective. To run the pattern, we first activate it, and now using this button up here, we can play the full log through the pattern. You can see that LogAn has found 2740 tests. We show them, and you see a lot of tests being identified all over the log. Right, they are a bit too small to see, so let's zoom in, and let's then just select any one of these and see what it gives on the right hand side. Now you see that the lines which are used for this test are marked in red, and you see that this test was a test with sequence number 1. And if we click the second here on the left, we see that that one has sequence number 2 assigned to it. So what did we see here in the first pattern definition? We saw that you can visually define a pattern using those expressions, that you get a quick visual overview of the logs, and you saw all tests being identified, and we will show more in the next demonstrations. Once we have generated events like the test event, we can start doing useful stuff with it. For instance, finding gaps between such tests. We remember the initial question: when did an operator hesitate more than 2 minutes between tests? This will now be very quickly done, and probably you already know yourself how to start on it. Yep, you guessed it. We create a new pattern definition. And call it the test gap pattern. Back to the editing perspective, here we go. Again, we select the Esper main statement, and now we are consuming only the previously defined tests. Also here we use the streams, and we edit it using the last tab. We are now looking for, in fact, a test followed by a test, so we define a followed by expression. We drag in 2 filters. The first filter is of type test, of course it is, and we call it test1. The second filter is also type test, test and we call it test 2. So we have to restart on every test because we want to see the difference between every test. And now we go to the match handler. Okay, let's add an event generator. We don't have the correct type yet, so we need a new event type definition. And we call this test gap. No properties required, so our event generator can just start using this new test gap pattern event. The start time is the stop time in fact of the first test, so test1.stop time, and the stop time is test2.start time. Here it can be interesting to use the feature of variables. So let's add here a new variable and we call it test diff, which is the difference in test time. So let's say the value of this is the test2.start time minus the test1.stop time. Or maybe it's a better name if we would write gap size. It represents the size of the gap after all. When do we want this kind of event to be triggered? Well, when this gap size exceeds 2 minutes. So gap size is bigger than 120,000 milliseconds. The L stands for Python long. And we can even assign severities. For instance, we will add severity if the gap size exceeds 20 minutes, 120,000 and an additional 0. We call this kind of gap a critical one, and all the others we consider them as just a warning. Voilà, and again here the sub-events, we derive them from the stream. Test1, test2 automatically filled in, rename 1, 2, and that's it. Again, let's save the pattern, return to the play perspective, activate the pattern, and rerun. So you can see 7 warnings have been identified and 2 critical ones. Now if we show them, we don't see anything, but we have to zoom to fit because there are only a few in the full scale. So we see a severe one there, a critical one there, which has taken 34 minutes, 4 seconds and so on. So if we now expand this event, it will start pointing to the 2 events that it was derived from. I don't know whether you have timed this part, but it took us about 5 minutes to define this pattern, so that's quite quick. And once you have done the previous stuff and you own the information on events and you have identified events, then it goes fast. Yet some other interesting features can be shown in the following demo. Here we look for the start of a new batch. As indicated before, each new batch starts with a sequence number equal to 1, but because of communication issues, this machine could miss some batch numbers. Essentially that means it could also start with a sequence number 2 or 3. So how will we solve this? First, let's look at how the sequence number evolves through the test. That's easy, just drag in the sequence number into the tracing area and you immediately see the evolution going up, going down. At the time of the gap it stops a bit, but then it's up and down and up and down again. So that's how the sequence number evolves. Now again we are in fact looking at differences between the sequence numbers of 2 consecutive tests. That looks very much like the comparison of the timestamp between 2 consecutive tests, so we could as well just duplicate the test gap pattern to get started with the new pattern here. and we will rename it and we will call it a sequence anomaly pattern. We open it for editing and we keep most of the stuff. We will in fact only modify the event generator to generate now a new event type, being an event type for the sequence number anomaly. So sequence number anomaly, and we assign it two properties, being the sequence number for the first one, an integer and 0 as a default value, and the second observed sequence number, also an integer, also default 0. Well, and we just switch the event generator to the newly created sequence number anomaly here. Condition is not relevant anymore. Start time, stop time is still okay. And this we don't need. We fill in this as test1.sequence number and the other one as test2.sequence number. We will in fact only need anomalies. We should consider only anomalies if the test1.sequence number plus 1 is different from the test2.sequence number. So the normal order in this is not respected, and then we don't need the severity anymore. So we save, we activate, go to the play perspective and run again. And you see 104 sequence number anomalies, which is quite a bit of communication issues here. Now let's add the pattern again and add a severity here below. When it seems that the sequence number is dropping, we consider this as being a harmless anomaly, because in fact that is the one which is indicating a new batch. So we select harmless from the list. Voila. And let's run again and show the results. So now we have 99 default values and 5 harmless anomalies. So at 5 locations you see that the sequence number is really dropping. So in fact at 5 locations we will have a new batch being started. We can now use this information to visualize batches like this one, containing all the tests inside. Again, we should then create a new pattern, and this time we call it the batch pattern. We edit it. Similar to before, we choose the as per main statement, and we will now be using tests and also the previously defined sequence number anomalies. For the stream, again the pattern stream, and here we are in the editing screen. So we are again looking for a followed by expression. What will we put in there? We are looking for a sequence number anomaly in fact. But the batch can also start at the start of the log file, and so in fact we are first looking for either the start of play, the start of the log file, or a filter which indicates a sequence number anomaly. So the first filter we take a start of play, and for the second filter we select the sequence number anomaly. And of course not any sequence number anomaly will do. We only want to see those in which the second sequence number is 1. This is a shortcut in fact, because we know that the sequence number 1 or 2 or 3 even could be gone because of communication errors. Next we should be collecting all the tests within the batch. So we add a filter and we make it of type test, and we assign it test as the name for future reference. And we do not want to collect only one, no, it could be 0 or it could be whatever as an upper boundary. And we only stop at the end of the batch. And again, just like the beginning, the end of the batch consists of potentially two parts. Either, like we indicate here, it ends with the end of the log file, or it ends with a sequence number anomaly with the identical condition as before, being the sequence number 2 of that anomaly should be 1. And you know by now that something is missing. Once we have encountered such a start trigger, either one of these two, we need to restart the full expression and start looking for potentially a new batch. The next part of a pattern is always the match handler. So again, here we add an event generator and we provide a new event type definition with the name batch. In this case, the useful parameter would probably be the batch size. So let's just take size here, being an integer and a default value of 0, representing the number of tests within the batch. So the event generator could now create such a batch event. Start time is the start of the first test, and the start time of the first test in the list. And the end time, the stop time, is the -1 element of the array, and Python syntax for the last one. And the size, let me make some room, the size is the number of tests, so the length of the test array. We can store all the tests as sub-events for this batch event, and for now that's it. So let's just run it again and see where it brings us. We activate the pattern. Oops, we do have a mistake here. So LogAn puts a red cross. What is wrong? He says, oh, my double equals sign is incorrect. It seems I made a typo, so let's edit again. It brings us to the location of the error, which is in this case the pattern stream syntax. So let's look at the graphical thing, and yeah, clearly I have put two equation signs there, which is not correct according to the syntax of Esper. So that is fixed. We save it again, no error anymore. Play, run, voila, replay the buffer. And here we are, we find 6 batches. Let's visualize them. And you see here we do have 6 batches. If we click such a batch, we also see the batch indicated on the timeline like any other event, and we can see the events evolving within the batch. Till now we have seen quite a few features of LogAn, but we didn't mention pattern mining yet. When we were defining the match provider of our patterns, we used the Esper main statement. Like for instance here in the test pattern on the match provider tab, we see match provider type Esper main statement. But LogAn also supports a different kind of match provider, which is the pattern mining. Let's now take a look in a bit more detail to the abilities of this pattern mining. So what do you need to do to use LogAn pattern mining? Well, you have to provide some example occurrences of what you're looking for, and LogAn will then try to find a regular expression that covers those examples. LogAn can additionally perform fuzzy matching in the sense that it will look for occurrences which are similar to what you're looking for, but not necessarily identical. The advantages of such pattern mining are obvious. In one sense, you do not need to learn an expression language to build your queries. You just use the examples. And on the other hand, the fuzzy matching can reveal unknown situations to you, unknown behavior of the machine which looks like what you expect, but which you didn't expect. We can show this based on the same example as we have been using in demo 2. So where we were trying to make the combination of the clamping object, the test start done, and the store and so on, and we tried to combine that into one test. We could now wonder, hey, did we do a good job when we defined this in Esper, or are we misunderstanding maybe or overlooking some parts of the machine behavior? So let's switch back to the LogAn application, and more specifically to the test pattern in the match provider tab. So like I explained earlier, we have been using the Esper main statement here in the past, and just for the memory, what did we do there? We defined a stream which started with a clamped on object, which was then followed by a sequence step on, step off, store on, store off, repeated multiple times till we encountered a save, so the storage of our test. That was our original definition. Now let's look for a way to do this in pattern mining. Suppose we didn't have this one. We can now create a new pattern definition, which we call similarly test pattern, and we just add PM for pattern mining. But now, instead of the Esper main statement, we will be selecting the pattern mining. It is more easy to edit this kind of patterns in the pattern mining perspective, so it's a perspective specifically made for pattern mining, so I'll switch to that one. Voilà, and here, like we explained before, the first thing to do is creating an example, selecting an example, in this case, for instance, from the log file, which is here on the bottom right hand side. An example would be here clamped on, followed by a step on, step off, store on, store off, and finally a save operation. So I just take these events and I drag them in as a example sequence. It's stored now here. I'll make this a bit smaller so that you can see it. So we now have a trivial example. Does it cover everything in our log? Certainly not, but it is an example. So let's try. I learn the regular expression that goes with this. Well, learning the regular expression is trivial in this case because it's just one example. So the main time that he spends here is now because of the computation of the statistics that we will be using within a second. Voila. So here are the statistics, and we see that we have been, here in the statistics window, that we have been finding a match with this kind of trivial regular expression, where you just have the 6 consecutive events. We have been matching 2140 events. Those events are considered consumed, but in fact we are skipping 700 events. Let's compare that quickly with the results of the original Esper pattern. We saw here that the test pattern matched on 2740 cases, which is clearly more. So, what are we missing? What are those 700 unconsumed events? Well, you see immediately here that there are still quite a bit of step-ons, about 900. So that would mean that there are more step-ons than clamped on, and we already knew that machine behavior, and we already used it before. Step on, step off, the store on, store off, they could be reoccurring more than once within one test. So we will just, that's a trivial one, we will just add it as a new sequence. I make another example sequence and I manually compose it as it. Oh, that's not correct, of course. It starts with a clamped on, then it goes into step on, step off, store on, store off, and then a step on again, a step off, a store on, and a store off. Oops, here at the end, voila. And then it is ended with a save. Voila. So this is our new example going from clamped on to save. We learn the regex again. So here we are on the event type statistics. We see now that the clamped on object instead of the 2140 now reaches 2265 consumed events. So in that sense, by doing this small modification and by allowing a second iteration on the steps and stores, we have discovered about 120 additional events. So what else can we conclude from this? If you look at the regex statistics, you can clearly see that the 2265 consumed events are directly consumed steps or nested for the second iteration. So here you see more specifically that 125 of the tests have required a second iteration. Additionally, like we introduced before, LogAn provides partial match statistics, so statistics on a less correct match, fuzzy match, and LogAn orders these by rank. The rank gives a measurement for how well it matches the original regular expression. So 1 is a perfect match, and you see that 2140 perfectly match this regular expression in that way. If you look here, it's a bit strange. It shows that clamped on could be not matched there at the start. It's not just a subset because they are filtered out, and so for some reason he sees occurrences in the log that look like this but don't seem to match with a clamped on. And if we look a bit further down here, we see why. Because it seems that a clamped on could be followed immediately by a save. Now we can suppose that this save is the save of the previous test, which just happens after the start of the next step of the next test. So that is a strange situation which we didn't take into account yet. So let's try and see whether we can optimize this. Again, we could do this by adding an event generator here in the match handlers list, but based on this new knowledge that we have discovered with the pattern mining, for this particular case it's probably easier to say, hey, let me modify the originally defined test pattern and let me change the way that that we look at this. And because here we have said that we want to match on every sequence of clamped on going over all these till a save, while we now just concluded from the pattern mining that it could very well happen that they are a bit overlapping, so that every clamped on could be the start of a new pattern match and that the save will conclude potentially after the next clamped on. So how can we do that here? We just remove the flag every on the overall followed by, and we say no, please start looking again for a new test once you see a new clamped on. So on this clamped on I say that you have to start again. So this is the first modification, but now suppose that we leave it like this, then every clamped on will start a new match, but the save of the previous match will make this one terminate. That's of course not what we want. So let's exclude this situation and make sure that every save is preceded by at least a step on. And so we remove the save like it is here, and we say no, we will only stop at the moment that we discover a sequence of a step on. Well, we don't have to capture this one because we already have it here, followed by a save. So this now essentially means that every clamped on starts looking for this kind of sequence, and additionally it will immediately stop at the moment that it finds at least one step on, and then somewhere after that a save. So let's see what this modification does. We run it again, and suddenly we get 95 additional matches. And you also saw there was 99 here. In fact, almost all our sequence anomalies are now gone. So we have come to the end of this screencast. Let's draw some conclusions. Throughout the screencast we followed a typical workflow. We created a parser that typically happens only once for each kind of log file that you have, and potentially it even only covers a few of the initial lines of the log that you need, and you increase it afterwards when new requirements arise. Next, we presented a few questions that you could have on the log files. We've built patterns for them, and we obtained an answer for each one of them. Each one of those patterns typically generated events that were then used as input for a higher level pattern afterwards. And as you can see, every pattern can be used over and over again on the same log file or on different log files. The main features shown in this screencast are: first, the powerful pattern definition that allows you to create advanced queries. Second, you saw that you can reuse previously defined patterns for any future analysis. You can interactively visualize higher level events, like for instance we saw the full tests instead of the individual log lines involved in one single test. And the fuzzy matching that we showed at the end allows you to discover situations that are similar to the things that you're looking for, but not exactly the same. All this allows you to enhance the log file value for your developers and for the support engineers, because they can now easily recognize well-known production issues, for instance, and they can quickly add their own queries and so on. Okay, so if you're interested in the product or you have questions concerning it, do not hesitate to contact us on the email address info@fmtc.be. Thanks, and hear from you soon.